Hello everyone. This is Professor Deepika from Department of Electrical and Electronics Engineering of Sai Vidya Institute of Technology. In previous video, we were discussing about the problems or the numericals related to tractions, and also which is related to a specific energy consumption and the tractive effort. So that we have actually we have solved some 4 problems related to that. In this video, let us solve some of the problems some of the other problems related to specific energy consumption and the tractive effect. So in the last video, we have solved the 4th problem. So let us move on to the 5th problem. The speed time curve of an electric train on a uniform rising gradient of 1 in 100 comprises uniform acceleration from rest at 2 km per hour per second for 30 seconds. And the second one, they have given coasting with power of for 70 seconds, braking at 3 km per hour per second to standstill. And the weight of the train is 250 tons. The train resistance on a level track being 5 kg force per Newton, and the allowance for rotary inertia is 10%. Calculate the maximum power developed by traction motors and the total distance traveled by the train, assuming transmission efficiency as 97%. So this is the given problem. So here they have not specified which type of curve it is, but when you look at the coasting period, you have to get to know that it is a quadrilateral curve. It is not a so please remember, in a quadrilateral curve they will be specifying the coasting data, whereas in the trapezoidal curve they will not be mentioning any coasting data. So hence we will get to know which type of curve it is. So therefore it is a quadrilateral curve, and with respect to that only we have to use the formulas. So first, let us understand the problem. So here they have given the speed time curve, and we got to know that it is a quadrilateral speed time curve, and they have given the gradient, and also they have given the acceleration period and acceleration coasting period they have given, and the braking retardation, that is the deacceleration also they have given, and the weight they have specified, and the train resistance, and the allowance of rotary inertia, and the efficiency they have given. But we have to calculate the maximum power developed by the traction motor. So let us list out the data. So gradient is nothing but what? It is 1 by 100 of usually, so that we are going to take. So percentage of 100. So hence it will be 1%, and the alpha is 2 km per hour per second, and T1 is 30 seconds, and T2 it is 70 second, and beta it is 3 km per hour per second, and the weight 250 ton, and the resistance here please note that they have given in kg per ton. So before solving the problem, we have to look on to the units also, because units are very important. The same unit we are going to use in the problem, so that we have to make sure. So here they have given the kg per ton, but we have to convert it into Newton per ton. So please remember this. So hence to convert it into Newton per ton, we have to multiply the resistance value with 9.81. So hence it is being converted into a Newton per ton. And the effective weight, it is usually W plus 0.1 W, which is nothing but 1.1 W, which is nothing but 1.1 into 250, and efficiency eta is nothing but 97%. So before solving the problem, we have to look on to the what is the data we need to calculate. So they have told you to calculate the maximum power developed. So the maximum power developed we have to calculate. So before that, we have to know what is the maximum power output at the driving axis. So that we know that maximum power output at the driving axle is nothing but Ft into Vm divided by 3600. So before calculating tractive effort, we also have to calculate Vm. So that I have not shown you in this step. So how do I calculate Vm? So Vm can be calculated by using the formula, that is acceleration. We know that it is nothing but Vm by T1, that is alpha is equals to Vm by T1. So here alpha is given and T1 is given, and we could actually calculate Vm. So Vm is nothing but 60 kilometer per hour. So hence we have calculated the Vm also. And as I told you, the formula is Ft into Vm divided by 3600, which is the maximum power output at the driving axis. So hence, let us substitute the value. So before that, we have to calculate the Ft, that is tractive effort. So the formula for tractive effort, Ft is nothing but what? It is nothing but 277.8 We alpha plus 98.1 Wg plus Wr. So let us substitute the data, hence we will get the value which is nothing but 1,89,577.5 Newton. So maximum power output from driving axis, which is nothing but Ft into Vm by 3600. We know Ft and Vm is 60 km per hour. Let us substitute, we will get the value 3159.625 kilowatt. So maximum power developed by the traction motor we have to calculate. So what is the formula for it? Which is nothing but power output by efficiency. So to calculate the maximum power developed by the traction motor, so we have to do in this way, that is nothing but power output by the transmission efficiency. So which is nothing but 3257.3456 kilowatt. So this is the maximum power developed by the traction motor, but this maximum power the fully will not be transferred to the driving axis. Hence the maximum power output from the driving axles will be less, because due to wear and tear of motor and wear and tear of wheels and all, the efficient the transmission, like the power output will not be exactly same as by the traction motor at the driving axles. So next we have to calculate the total distance traveled by the train. So to calculate that, we have to know V1. So V1 we got to know, which is nothing but 60 km per hour, and we also have to know V2. So V2 is nothing but what? It is the velocity at the braking period. So to calculate V2, we have to know the braking retardation beta C, or the coasting retardation beta C we have to calculate. So for that we know that it is nothing but Ft is equals to, instead of alpha we have to use minus beta C, because it is in decreasing manner, and in the coasting period we are not going to apply any power, hence the tractive effort will be zero, because the train will be running under its own momentum. Hence Ft will be zero now. So let us substitute Ft as 0, and all the data we know, let us substitute, and hence beta C is nothing but what? It is nothing but 0.4815 kilometer per hour per second. So therefore V2, how do we calculate? Which is nothing but V1 minus beta C into T2. V1 we know, beta C we know, T2 we know. So let us substitute. Hence we will get the V2 as 26.295 kilometer per hour. So which is the data. And we also have to calculate the braking period. So braking period is nothing but T3 is equals to V2 by beta, which is nothing but 8.765 seconds. So what is the total distance traveled by the train, which is nothing but V1 T1 divided by 7200 plus V1 plus V2 into T2 divided by 7200 plus V2 into T3 divided by 7200. So this we have derived in the quadrilateral curve. So this formula we are going to use now. So to calculate the total distance traveled by the train, we have to calculate V1. So which so as I told you, it is calculated by alpha into T1. Hence we have calculated V1 T1. To calculate V2 we have to know beta C. Hence we have calculated beta C also, and T3 also we have calculated. So let us substitute the values. Hence the total distance traveled by the train will be 1.121 kilometer. So next, this completes the problems on specific, specific output and all. So now let us solve the problems related to specific energy consumption. So first problem is going in this way. An electric train has an average speed of 42 km per hour on a level track between the stops 1400 meter apart. It is accelerated at 1.7 km per hour per second and is braked at 3.3 km per hour per second. Estimate the energy consumption at the axle of train per ton kilometer. Take tractive resistance constant at 50 Newton per ton and allow 10% of for rotational inertia. So here, so read out the problem again. The average speed they have given, which is nothing but 42 km per hour, and the distance between the stops they have only given, which is nothing but 1400 meter apart, and we have to and the train is accelerated, that is the alpha value they have given, which is nothing but 1.7 kilometer per hour per second, and the braking retardation they have given, um, which is nothing but 3.3 kilometer per hour per second. Estimate energy consumption at the axle. So we have to calculate what is the energy consumption. So till now we have solved the problems on specific energy output, but here we have to actually have to we are going to solve on a specific energy consumption. Okay, so our energy consumption, so we have to calculate axle at the axle of train per ton kilometer we have to calculate, and the tractive resistance they have given directly, we need not to multiply by 9.81, so hence the value is again 50 newton per ton. And the rotational inertia they have given, we have to allow a 10% inertia. So let us list out the data first. So that is the average speed they have given, which is nothing but VA, which is nothing but 42 kilometer per hour. And the distance they have given 1400 meter, but we need to convert it into kilometers. So let us divide by 1000 to get into kilometer. Hence it is 1400 meter. Okay, so this is the thing, sorry, 1.4 kilometer, and alpha is nothing but what, which is nothing but 1.7 kilometer per hour per second, and beta is nothing but what, it is 3 kilometer per hour per second, and R they have given, which is nothing but 50 Newton per ton. So that is 10% inertia we are going to add. So hence effective weight W E will be W plus 0.1 W, which is nothing but 1.1 W, or we can have a ratio, so that will be better. So instead of and the weight of the train value they have not given. Hence, the ratio of this WE and W will be what? It is nothing but 1.1. So this is how we have listed out the data. So next, we actually calculate the energy consumption, correct? So to calculate the energy consumption, just a minute. So first let us calculate this data, that is total time for run we have to calculate. So the total time for run, that is T, that is capital letter T, which is nothing but what? So we can, because they have given the average speed, hence we could actually calculate the total time for run, which is nothing but 3600 D divided by VA, which is nothing but what? 3600 into 1.4 divided by 42 will give you the value 120 second. So hence this is the hence we have calculated the total time for run. Okay, so hence we have calculated the capital letter T, because why we have to calculate all these data means the total like the energy consumption formula we have in this way, that is 0.01072 Vm square divided by D into W E by W plus 0.2778 R d1 by D. So this is the value. So in that we can actually calculate the Vm also. So Vm we could calculate easily. That is to substitute all these values, we have to calculate the first these things. That is, we have to calculate the maximum speed, we have to calculate the total distance between the stops and the D1 and the capital letter D. Hence to calculate that, first let us calculate the total time for run. So which is calculated by this formula, that is 3600 D by VA, hence it is 120 second. And first let us actually calculate the K value, because it is 1 by alpha plus 1 by beta, which is nothing but 500 by 561. And the maximum speed Vm, how do we calculate? Which is nothing but T by K minus 1 minus T by K whole square minus 7200 D by K. So this we have derived in the derivation on trapezoidal curve, correct? So that is the maximum speed with respect to the trapezoidal curve. So that formula we are again using. So let us calculate this. So T we have, K we have, and the total distance D also they have given. So let us substitute the data. Hence we will get, which is nothing but 52.0677 kilometer per hour is the maximum speed. Hence, we have calculated the maximum speed. So next, they have given the acceleration period we need to calculate. So which is nothing but T1 is equals to Vm by alpha. So hence it is 30.6280 second. So breaking period, that is nothing but T2. Sorry, T3. So T3, how do we calculate? Which is nothing but Vm by beta. Hence it is 15.7780 second. So then how do you calculate the T2? T2 is nothing but total time for run, that is T minus T1 plus T minus of T1 plus T3. Hence free running period, that is T2 is nothing but T minus of T1 plus T3. So hence it is 73.594 seconds. Then distance traveled during braking, that is nothing but that is how we could calculate, which is nothing but V2 T3 divided by 7,200. So please refer the derivation. So hence we could actually calculate the distance traveled during braking. Hence it is 0.1140 kilometer. And D1, so D1 is nothing but what? So D1, it is nothing but it is the distance traveled during acceleration period, correct? So how do we calculate or the acceleration and the free running period? That is the distance when the power is on. Hence, D1 is nothing but what? It is the total distance D minus distance traveled during braking. So which is nothing but what? 1.286 kilometers. So this is the distance traveled during acceleration and the free running period, or we could say the distance traveled during the power is on. Hence, the total the energy consumption at the axle of train per ton kilometer. So how do we calculate it? So we have a formula. So that is 0.01072 into Vm square divided by D into We by W plus 0 point, sorry, here point is missing, 0.2778 R D1 by D. So hence we have calculated the Vm by the derivation formula, and we know the ratio We by W. D is given in the problem, and D1 hence we have calculated in the previous step. So let us substitute the value, which is nothing but 35.5928 watt hour. So this is the energy consumption at axle of train per 10 kilometer. In this way, we can calculate the energy consumption. So let us move on to the next problem. Calculate the specific energy consumption if a maximum speed of 12.2 meter per second and for a given run of 525 or 500 to 25 meter, an acceleration of 0.366 meter per second square are desired, and the train resistance during acceleration is 52.6 Newton per 1000 kg, and during coasting it is 6.12 Newton per 1000 kg, 10% being allowable for rotational inertia, and the efficiency they have given, which is nothing but 50%, and they have also, and they only mentioned that it is a quadrilateral curve, or assume it is a quadrilateral curve. So again we have to calculate the specific energy consumption. So again, to calculate the specific energy consumption, we have to calculate the specific energy output first. To calculate the specific energy output, we have to calculate the total energy required during the run. So then to calculate the total energy required during the run, we have to calculate the tractive effort. So therefore, we will be going on step by step. Correct. So let us list out the data. W by W is again, it is 1.1. Alpha is given, which is nothing but 0.366 meter per second square. And Vm they have only given, but which is nothing but 12.2 meter per second. And distance D they have given 1525 meter, which is nothing but 1.525 kilometer. The train resistance during acceleration they have given, which is nothing but R is equals to 56 Newton per 1000 kg. But it is usually in terms of like we are going to calculate in terms of Newton per kg. Hence, let us multiply by. Hence, we have to divide, or we could actually write it again, because 1 ton they have directly given, which is nothing but 52.6 Newton per ton. Instead of Newton per ton, which is nothing but 1000 kg, they have written. Hence, it is nothing but 0.0526 Newton per kg. and the tractive effort we have to calculate, which is nothing but here the gradient they have not given, correct? Hence the gradient value is 0. Hence we need not to use 98.1 Wg term. Hence it is 0. Hence we have used only We alpha plus Wr. So We, we know that it is nothing but 1.1 W, and alpha it is 0.366 plus radiance resistance is 0.0526 hence upon calculating we will get the value 0.4552 W Newton. So here we don't know the weight of the train, let us retain as it is, so which is nothing but W Newton. And the total energy required for the run we have to calculate it. So which is nothing but what? It is nothing but energy required during acceleration, as there is no free run because it is a quadrilateral curve. Here there will be a only acceleration period and the coasting period will be more, and there will be a braking period. Hence the total energy required for the run is nothing but only the total energy required during acceleration. So how do we calculate it? So energy is nothing but what? It is nothing but power into time. So hence we could write as average power during acceleration into acceleration period. So how do we calculate the average power during acceleration? Which is nothing but half into Ft into Vm into T1. So this is nothing but the average, like power is nothing but what? Average power is nothing but half into Ft into Vm. That is force into force into the maximum speed, and the acceleration period is nothing but t1. Let us substitute here. So hence we will get in terms of joules, or we it is usually watt second. So next, to convert it into watt hour, we need to divide by 3600. Hence, it has been converted into watt hour. Again, W is retained as it is because we don't know what is the weight of the train. Next, we need to calculate the specific energy output. So how do you calculate the specific energy output? Specific energy output is nothing but what? It is nothing but the total energy divided by W into D, correct? So that is the formula to convert the energy output into specific energy output. To convert it into specific energy output, whatever the output we will get from the total energy required for the run, we have to divide by W into D. So let us do it again. So therefore W and W get cancelled. Hence we will get the value 1.6839 into 10 to the power of 5 watt hour. It is not W again, it is watt hour per kg meter. So this is the specific energy output, because W and W will get cancels out here. So W will get cancels out here, and it is actually the unit. So, but we have to calculate the specific energy consumption. So, what is the specific energy consumption? Which is nothing but specific energy output divided by efficiency. Hence, it is 3.3678 into 10 to the power of 5 watt hour per kg meter. So next we will move on to the next problem, that is an electric train has quadrilateral speed time curve as follows. First one, uniform acceleration from the rest, that is the acceleration given 2 kilometer per hour per second for 30 seconds and coasting for 50 seconds, braking period of 20 seconds. The train is moving a uniform up gradient of 1%. Tractive resistance is 40 Newton per ton. Rotational inertia effect is 10% of dead weight, and the duration of station stop is 15 seconds, and the overall efficiency of transmission and gear motor as 75%, and calculate the value of its scheduled speed and specific energy consumption of the run. So again we have to do the same thing. Again, to calculate the specific energy consumption, we have to know what is specific energy output. So to calculate specific energy output, we have to calculate again the energy required for the run. Again, to calculate the energy required for the run, we have to calculate FT, VM and all. So let us list out the data. Alpha is 2 kilometer per hour per second, and T1 is 30 second. T1 is 30 second, and T2 is 50 second, T3 is 20 second, G is 1%, resistance is 40 Newton per ton, WE is 1.1 W, stop time they have given, which is nothing but 15 second, and eta is 0.75. So first, let us calculate the maximum speed V1, correct? So V1 is nothing but what? It is nothing but alpha into T1. Again, it is 60 kilometer per hour. Again, you have to remember this thing, that is for the up gradient you have to use positive sign, for the down gradient you have to use the negative negative sign. So let coasting retardation be beta c, and again the same formula, ft is equated to 0, that is static effort will be 0 during coasting period. So hence we have calculated beta c, which is nothing but 0.4519 kilometer per hour per second. So next we know that V2 is nothing but V1 minus beta C into T2. So hence it is nothing but what? V2 is equals to 37.405 kilometer per hour. So V1 we got to know easily, it is nothing but alpha into T1, but to calculate V2 we have to know the braking, that is the coasting retardation beta C. Hence we have calculated the coasting retardation also. Next braking retardation we don't know, to calculate it beta is nothing but V2 by T3. Hence it is 1.87025 kilometer per hour per second, and the total distance traveled is nothing but this formula, which is being derived in the quadrilateral curve derivation. So next substitute all the data, hence it is 1.0303 kilometer. Again scheduled time we know we have to calculate, because they as been the problem we have to calculate the scheduled speed also. So to calculate scheduled speed we have to know scheduled time. Hence TS is nothing but total time for run plus the total time for run plus duration of stop. Hence it is nothing but T is nothing but T1 plus T2 plus T3. So hence it is 115 second. Scheduled speed is nothing but what? It is Vs is nothing but 3600 B by Ts. Hence it is 32.2528 kilometer per hour. Hence we have done with the one part of the problem. So let us move on to the next problem, next part of the problem. So that is we have to calculate the D1, that is distance traveled when the power is on. To calculate it, it is nothing but distance traveled during only the acceleration period. Hence, it is only V1 T1 divided by 7,200, which is nothing but 0.25 kilometer. Specific energy output, we have this formula. So substitute the value. And please remember, in the last problem, they have not specified the gradient. Hence, we have not used this formula. That is 0.2778 into 98.1 G, we have not used. But here the gradient they have specified, but hence we have to use this thing. So we have all the data, substitute over here. Hence the value we will get is 50.5117 watt hour per ton kilometer. So next specific energy consumption, it is nothing but specific energy output by efficiency. Hence it is 67.3489 watt hour per ton kilometer. So next we have third problem. Again, the third problem is also a similar way. So you can go through it. That is an electric train weighing 100 ton. Here the W weight they have specified, and the rotational inertia is 10%. This train, while running between two stations which are 2.5 kilometer apart, 2.5 kilometer apart, has an average speed of 50 kilometer per hour. The acceleration and retardation during a braking are respectively 1 kilometer per hour per second and 2 kilometer per hour per second. The percentage gradient between these two stations is 1%, and the train is to move up the incline, and the train track resistance is 40 Newton per ton. If combined efficiency of electric train is 60%, determine the maximum power at the driving axles and the total energy consumption, specific energy consumption. Assume the journey estimation is being made on simplified trapezoidal speed time curve. So here they specified that it is a trapezoidal speed time curve. So therefore we have to solve with respect to the trapezoidal speed time curve. So let us list out the data. Next, the duration of run we have to calculate, which is nothing but capital letter T. Here the average speed they have given, hence it is calculated as 3600 D by VA, which is nothing but 180 second. First let us calculate K, because VM, that is the maximum speed in trapezoidal curve, will be calculated by the formula T by K minus T by K whole square minus 7200 D by K. Hence we have to calculate the T and K. So maximum speed is nothing but this formula. Substitute, you will get the value 71.0102 kilometer per hour. And acceleration period T1 is nothing but Vm by alpha. which is nothing but 71.0102 second. And breaking period T3 is nothing but Vm by beta, which is nothing but 35.5051 second. And time for free run, that is T2 is nothing but T minus of T1 plus T3, which is nothing but 73.4847 second. Next, tractive effort we need to calculate, which is nothing but this formula. So substitute, we'll get the value 44,368 Newton. And the maximum power at the driving axles we have to calculate. So what is the formula, which is nothing but Ft into Vm divided by 3600. Substitute, we'll get the value has 875.1612 kilowatt. Total energy output we have to calculate. So which is nothing but it is the energy during run as well as during coasting also. So hence we have to write this formula. So where Ft dash is nothing but what? It is the tractive effort required during free run. Hence, and it is equal to only 98.1 Wg plus Wr. Remember, Ft dash is nothing but what? It is the total tractive effort during free run. It is the total tractive effort during free run. Hence, we have to take only this term. Whatever the acceleration we have, so that will be 0 here. Okay, so therefore we are taking in this way, that is only total time for free run we have taken. So let us substitute the value. So hence total energy output is nothing but 14.1917 kilowatt hour. Next we have to calculate the total energy consumption, which is nothing but total energy output by efficiency, which is nothing but 23.6528 kilowatt. So specific energy consumption is nothing but what? It is the total energy consumption in watt hour divided by weight of train in tons into distance of running kilometer. Hence it is 94.6112 watt hour per ton kilometer. So next we have the other problem. So other problem is also in the similar way. So you can refer the PPT and you can easily understand. Again, we have used the same formulas. So next we will discuss the fifth problem. It is proposed to put an electric trolley service in a city. In a city, the scheduled speed is to be 45 kilometer per hour. The distance between the stops is 2.8 kilometer, and the track is assumed to be level. Each stop is of 30-second duration. Using simplified speed time curve, calculate the maximum speed assuming acceleration to be 2 kilometer per hour per second and retardation is 3.2 kilometer per hour per second. And the dead weight of the car is 16 ton. The rotational inertia is 10% of the dead weight, and the track resistance is 40 Newton per ton. If overall efficiency is 80%, calculate the maximum power output from the driving axle. Again, the specific energy consumption in watt hours per ton kilometer. So here you can see that here in a city they are going to plan the electric trolley service. Okay, so this is the proposed system they are going to tell you. So whereas they have considered that the scheduled speed would be 45 kilometer per hour and the distance between the stop is 2.8 kilometer and the track is usually a level track. And each stop they have told it is 30-second duration, and that means the trolley will be stopping only for 30 seconds at all the stops. And using the simplified speed time curve, we have to calculate the maximum speed and the acceleration and the retardation value they have given, and the dead weight is also they have given, and the track resistance also given. So, but we have to calculate the maximum power output and the specific energy consumption. So let us list out the data. First, we have to calculate the scheduled time for run because the scheduled speed is given, hence it is 224 seconds. Next, actual time of run, it is nothing but TS minus duration of stop. So, which is nothing but what? 194 seconds. Then K is nothing but what? It is 1.5. Substitute the data, that is nothing but 1 by alpha plus 1 by beta. Maximum speed, we have this formula, that is T by K minus T by K whole square minus 7200 D by K. Substitute all the value, hence you will get the value 59.3299 kilometer per hour. Acceleration time, which is nothing but Vm by alpha, that is nothing but T1 is equals to Vm by alpha. Hence, it is 29.6649 second. Duration of braking we have to calculate, that is nothing but Vm by beta, which is nothing but 18.5405 second. T2, how do you calculate? That is time for free run, that is T minus of T1 plus T3, which is nothing but 145.7946 second. And the tractive effort during the acceleration, so remember, it is only the tractive effort during acceleration. If they ask you the tractive effort during free run, then you need not to add the acceleration term. So the tractive effort during acceleration is nothing but 277 WE Vm alpha plus WR. Substitute all the data. Hence, you'll get the value 10,018.56 Newton. Then maximum power output, again the same formula, Ft into Vm by 3600, which is nothing but 171.703336 kilowatt. Again, the distance traveled during braking period we need to calculate, which is nothing but half into Vm by 3600 into T3 by 3600. So please thorough with the derivations, whatever we have solved in the last videos, because only from the derivations only we are going to take the formulas. Okay, so therefore this will be very important. Hence, the value D3 is nothing but 0.1527 kilometer. Distance traveled during with the power on, that is D1 is nothing but D minus D3, because in the coasting period, the braking period, power will not be on. Hence, we have to subtract from the total distance. Hence, you will get the D1 as 2.6473 kilometer. Again, the specific energy output, we have the formula. Substitute all the data what we have got. Hence, the value is 25.3303 watt hour per ton kilometer. Again, to calculate the specific energy consumption, again it is output by efficiency. Hence, the value is 31.6628 watt hour per ton kilometer. So this is how we have calculated. Next, we'll move on to the last problem on the specific energy consumption. That is, an electric train weighing 200 tons run a uniform up gradient of 1% with following speed time curve. Uniform acceleration of 2 km per hour per second for 30 seconds, constant speed for 40 seconds, coasting for 30 seconds, braking at 2.5 km per hour per second to rest, stop at station 15 seconds. If tractive resistance is 40 Newton per ton and the rotational inertia effect is 10% of dead weight and overall efficiency of transmission and motor is 75%, determine schedule speed, specific energy consumption and the total energy consumption and the distance between the stops. So let us list out the data. Speed at the end of the acceleration, first we have to calculate, because it is a quadrilateral curve. How do I get to know it is a quadrilateral curve? Because they have mentioned as coasting word over here. So when coasting period or coasting retardation, whatever may be the word comes, so that means it is a quadrilateral curve. So V1 is nothing but what? Alpha into T1, which is nothing but 60 km per hour. And to calculate V2, we have to know what is coasting retardation. Hence, let us use the tractive effort formula. Ft is equals to 277.8 We minus beta c plus 98.1 Wg plus Wr. Tractive effort is 0. Hence, beta c is nothing but 0.459 km per hour per second. Next, speed at the end of the coasting period we need to calculate, which is nothing but V1 minus beta c into T3. Hence, it is 46.443 km per hour. Hence, braking retardation, T4 is nothing but V2 by beta, which is nothing but 18.5772 second. Then we have to calculate the total distance traveled. I know V1, T1, T2, T3 and V2. So substitute all the data. Hence, it is 1.48 km. Hence, the distance traveled during when the power is on, D1 we have to calculate, which is nothing but only during acceleration. So you can see here, it is during only the acceleration period we have considered and this period. Correct, acceleration period and the free running period. Hence, we have taken only this value. Hence, it is 0.9166 kilometer. Schedule speed is nothing but what? Vs is nothing but d by 3000, d into 3600 divided by T1 plus T2 plus T3 plus T4 plus stop duration. Hence, it is 39.887 km per hour. Specific energy output, again we have this formula. So substitute all the value. which is nothing but 52.4431 watt-hour per ton kilometer. Specific energy consumption, again we have to divide by efficiency, that is specific energy output should be divided by efficiency, which is nothing but 69.9241 watt-hour per ton kilometer. Total energy consumption is nothing but what? It is nothing but specific energy consumption into W into D. So here you can see here specific energy consumption we have calculated. To calculate only the energy consumption, we have to multiply specific energy consumption into W into D, that is weight of the train into distance traveled. So hence it is 20.697 kilowatt hour. So we have to draw the graph also. So this is a speed time curve because it is a speed in y-axis and the time in x-axis. And we know T1, T2, T3, T4, everything we know. So let us mark this value. And the speed V1 is nothing but what? Which is nothing but 60. And V2 we have calculated, right? Which is nothing but V2 is nothing but what? It is nothing but 46.443. So hence it will come in this way. Hence we have drawn the quadrilateral curve. So this completes the problem on specific energy consumption. Thanks for watching the video.